everyone. You're watching the 32nd lecture for the course Mathematical Methods for Economics. And in today's lecture, we will talk about a general series, a general infinite series in particular. In fact, if you have reached this stage of studying a series, you would already know that a series is the sum of the numbers, the sum of the terms in a sequence. So, a sequence is an ordered listing of numbers. It's a listing of numbers in a particular order, and the sum of those numbers in the sequence, that is a series. You can actually view the results for an infinite geometric series in my previous video, but for the present discussion, note that we will be discussing a general infinite series, not necessarily a geometric series, though the results for the general infinite series, the results that we get, will also apply to a geometric series as well. Again, the focus in our lecture today will be on convergence and divergence. So, the question here is, what does it mean for an infinite series to converge or diverge, and if it converges, what is the sum that it converges to? And there is a vast literature out there, and there are many tests for convergence or divergence, but what we will do is, we will establish some criteria for convergence or divergence, but there are also some nuances that are involved here. So, you must pay special attention to the details as we proceed in this discussion. Let me first introduce the notation for a general infinite series to you. Suppose A sub 1 represents the first term, A sub 2 represents the second term, and so on. Let's take A sub n to represent the nth term in general. So, a general infinite series is given by the sum A sub 1 plus A sub 2 plus A sub 3 and so on, where the terms continue indefinitely. Now, because we have an infinite series here and we are interested in understanding the sum of the terms in this series, and what this particular sum, whether it converges to a particular value or whether the sum just explodes to infinity or minus infinity. To understand these concepts, we are going to introduce the concept of what is known as a partial sum. Now, what is a partial sum? A partial sum is denoted by S sub n, and it represents the sum of the first n terms in the series. So, for example, if n is equal to 1, S sub 1 will simply be A sub 1 itself, S sub 2 will be the sum of the first two terms in the sequence, so A sub 1 plus A sub 2. Similarly, S sub 3 will be A1 plus A2 plus A3 and so on. So, we can define S sub n as A1 plus A2 and so on till An, that is the sum of the first n terms, and this in compact notation can be represented as summation A sub k, where k goes from 1 to n. What we are going to do is, because we want to understand what the sum of the infinite series is. So, for S sub n, once we have this S sub n, what we will do in our exercise, and this is the method of partial sums, we will get n to become larger and larger, and we will look at the limit of this partial sum. We will see what this partial sum S sub n tends to as n tends to infinity. That is going to be our approach. And from here, we can develop the preliminary definitions for convergence or divergence. So, if the partial sum S sub n, it tends to a finite value which is S as n tends to infinity, then we say that the infinite series converges to the sum S. So, here the sum S can be taken as a sum of all of the terms in the series. Okay? So, we have this very important result for the infinite series to converge to the sum S. The limit of the partial sum S sub n, which is the sum of the first n terms, as n tends to infinity. So, we have to get n to become larger and larger, and if that S sub n in the limit tends to this finite value S, we say we have convergence. However, if S sub n does not tend to a finite limit as n tends to infinity, so here we have that the limit is plus or minus infinity, which is to say that the limit does not exist, we say the series is divergent. So this is the crux of the method of partial sums, and if you have watched the previous video, which was on infinite geometric series, it was exactly this method that we had used to arrive at the summation formula for an infinite geometric series. So let us look at that. Let me walk you through it. Let me walk you through the summation formula for a finite geometric series and an infinite geometric series. We'll do it quickly, but it's important because then you'll get a sense of how this method of partial sums is used, and you'll also be able to link up what we had done in the previous video with what I have just explained. So remember, this is a criterion that if the limit of the partial sum as n tends to infinity is a finite value, we have convergence, and if it is if the limit does not exist, we have divergence. Okay. So now let's look at a finite geometric series first. So if you remember from the previous video, a finite geometric series is of the form a plus a times k plus a times k squared and so on till a times k to the power n minus 1, where a is the first term, k represents a quotient. So every subsequent term after the first term is multiplied by this quotient or the common ratio to get the next term. So and the general term here is a times k to the power n minus 1. So the partial sum for a finite geometric series is a plus a times k plus a times k squared and so on till the nth term a times k to the power n minus 1. Now the nice thing about the geometric series is that here we have a simple expression for the summation formula, and this is how we had derived it. So if I multiply both sides of the terms in equation 1 by the common ratio k, you might be comfortable with the notation r, that's perfectly fine. In this book that we use for this course, which is Sater and Hammond, they have used k, so I am sticking to that notation. So we have k times s sub n is equal to a times k plus a times k squared and so on till a times k to the power n. I have just multiplied throughout by k, right? And now if I subtract 2 from 1, I am going to get s sub n minus k times s sub n is equal to a minus a times k to the power n, because all the other terms will cancel. So a times k will cancel out with this a times k when you subtract this one, the one below. Similarly, a times k squared will cancel out a times k squared below. So in that sense, we get the partial sum, the expression for the partial sum s sub n as a times 1 minus k to the power n divided by 1 minus k, where k can't be equal to 1 because division by 0 is not defined. Okay. Now the question here is, what meaning can be given to the infinite sum? So if I have the infinite geometric series a plus a times k plus a times k square and so on, then how do we get an expression? Can we get an expression first of all for the infinite sum? And the answer here is yes. And how do we do it? So all we have to do here is we have this partial sum. So here that is given by a times the first term times 1 minus the common ratio to the power n brackets closed divided by 1 minus k. So all that we have to ask here is, what happens to this expression for s sub n as n tends to infinity, right? And here it is things are quite straightforward, because you can clearly see here that if the common ratio is between minus 1 and 1 in the sense that if the absolute value of the common ratio is less than 1, then clearly k to the power n would tend to 0, right? And in that case, we will have the sum converging to a divided by 1 minus k for an infinite geometric series. So this is a very clean result that we have, a very simple result, that the sum converges to a upon 1 minus k, which is a formula we use for the sum of an infinite geometric series when the absolute value of k is less than 1. However, if k is more than 1 or less than or equal to minus 1, there k to the power n will not tend to any limit, and there we will say that the series will diverge. So, let us summarize these results. If the absolute value of k is less than 1, we say the infinite geometric series converges. And what does it converge to? It converges to a divided by 1 minus k. Okay? That will give us a sum of the infinite geometric series when it converges. However, if k is greater than or equal to 1 or less than or equal to minus 1, which is to say that the absolute value of k is greater than or equal to 1, the infinite geometric series diverges, because k to the power n in this formula will this will just explode if you have, let us say, 2 and then n tends to infinity. So, 2 to the power infinity, that is just going to be a very large number, right. So, in this sense, the infinite geometric series diverges. We have these two end cases here, which I had talked about in the previous video, but quickly. So, k equal to 1, if k is equal to 1, that is something we have not taken into account for the formula of the first n terms sum. So, if k is equal to 1, then the sum of the terms, the n terms, is simply n times a, because your series would be a plus a and so on. So, for the nth partial sum, it will the sum would simply be n times a, and you can see that for an infinite series, as n tends to infinity, this will tend to infinity if a is positive, and it will tend to minus infinity if a is negative. Similarly, if k is equal to minus 1, then the sum will be equal to a if n is odd, because let us say you have minus k equal to minus 1, then your series will look like a minus a minus a. So, if n is odd, the sum, the partial sum would be a for the sum of the first n terms, and if n is even, so there your S sub n will be 0. So, clearly in this case you will be oscillating between a and 0, and you can't have a limit as n tends to infinity. So, the point is that whichever case you are looking at here, k greater than or equal to 1 or k less than or equal to 1, your series will diverge. Right. Now, let us come back to a general infinite series discussion. Now, the claim that I have here is that if the series a1 plus a2 plus a3 and so on, if this series converges, then it must necessarily be true that the nth term tends to 0 as n tends to infinity. This is a very important result, and there are some nuances here which you must be very alert about. So, please pay attention. Now, our claim here is that if the series converges, then the nth partial sum S sub n will tend to a finite value, let us say S, as n tends to infinity. Here we can also argue that if the series converges, then the sum of the first n minus 1 terms will also tend to S as n tends to infinity. Why is that? Let us think of this intuitively, that if the sum of the first n terms tends to S as n tends to infinity, and we want that sum to stabilize. If I want the sum to stabilize, then as I go farther and further out in the series, then I must be adding something less and less, so that the sum changes only a little bit, so that finally it stabilizes. So, that is to say that if S sub n tends to S, the sum of the first n minus 1 terms will also tend to S as n tends to infinity. It may not exactly be S, but it will tend to S. And if I have these two criteria, then it follows that S sub n minus S sub n minus 1 will tend to 0 as n tends to infinity, right. Now, what is S sub n minus S sub n minus 1? S sub n minus S sub n minus 1 is nothing but the nth term. The nth term tends to 0 as n tends to infinity. So, our result here is that if our general infinite series a1 plus a2 plus a3 and so on to an and so on converges, then it must necessarily be true that in the limit the nth term tends to 0. Okay. Now, remember, actually note here, and this is a part of your understanding from the section on logic also, that the nth term being 0 as n tends to infinity is only a necessary condition for convergence. What we are saying here is that if the infinite series converges, then it must necessarily be true that the nth term tends to 0. But this is not a sufficient condition. So don't use this as a condition. So if this is satisfied, if the nth term is 0, don't conclude that the series necessarily converges. It is not a sufficient condition. And to illustrate this, we'll show, let me show you an example of what is known as a harmonic series. This is given by 1 plus half plus 1/3 plus 1/4 and so on. The general term here is 1 by n. Now here you can clearly see that the nth term tends to 0. The nth term here is 1 by n and it clearly tends to 0 as n tends to infinity. But this series is not convergent. This series is divergent. Now how is that true? Let us see how the harmonic series is divergent. So what we will do here is, we will write the series as, we will write it in the following way. So if you notice, I have created parentheses for a certain set of terms. So I've collected some terms and I've done it in a systematic way. So I have 1 plus half, then I have 1 by 3 plus 1 by 4. So I have 2 terms in this first set of parentheses, 4 terms in the next set of parentheses, then 8 terms in the third set of parentheses, 16 terms in the fourth set of parentheses and so on. Okay. Now let's see the pattern that emerges. It's a very interesting pattern and once you get the hang of it, it's something you'll feel really kicked about. So if you look at this first set of parentheses, 1 by 3 plus 1 by 4. Now 1 by 3 is clearly greater than 1 by 4, right? Because 3 is smaller than 4, so 1 by 3 is more than 1 by 4. And the second term 1 by 4 is exactly equal to 1 by 4. So if I take the sum of the left hand side and the right hand side, can I say that 1 by 3 plus 1 by 4 is going to be strictly greater than 2 by 4, right? And 2 by 4 is nothing but half. So I have that 1 by 3 plus 1 by 4 is strictly greater than half. Now what is going to now happen is, all of these groupings that I have done, you see a very nice pattern emerging and you will see that all of these sets of numbers are more than half. I am just cheating a little bit and giving you the result in advance. So let's see in a bit now how that happens. Now let's look at the next set, the second set of parentheses where you have 4 terms. Now here the last term is 1 by 8. Start by taking the last term as the reference. So 1 by 5 is greater than 1 by 8. 1 by 6 is greater than 1 by 8, 1 by 7 is greater than 1 by 8 and 1 by 8 is equal to 1 by 8. So we have 3 terms which are greater than 1 by 8. So can I say that 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 together will be more than 4 by 8, because you have 4 terms, 3 of which are strictly greater than 1 by 8 and 1 is exactly equal to 1 by 8. So all 4 together will be strictly greater than 4 by 8 or strictly greater than half. Okay. Similarly, let's look at the next grouping. Here we have 8 terms. We have the last term is 1 by 16, so that will be a point of reference. 1 by 9, 1 by 10 and all of these terms, these 7 terms are all greater than 1 by 16. The last term is exactly equal to 1 by 16, so the sum, the entire sum is going to be greater than 8 by 16. There are 8 terms, right? And that is nothing but half. So it's a beautiful pattern that is emerging. And in the last case where you had 1 by 17 to 1 by 32, you will have 15 terms strictly greater than 1 by 32 and the last term exactly equal to 1 by 32. So the entire sum is going to be 16 by, it's going to be greater than 16 by 32 or greater than half. So what are we doing here? We have actually added a large number of groupings of terms which are all greater than half. So basically we are adding something more than half an infinite number of times for this infinite series. So clearly this series is going to be divergent. Now if you have the appetite for a little bit more math, let's look at things in general. So what I have done here is I have just given you the pattern that I have followed for this harmonic series. We have in the first set of parentheses 2 terms. So that's 2 to the power 1 terms. The last term is 1 by 2 squared. So I have just taken 1 more in the power for the number of terms. Okay. Similarly, for the second set of parentheses, I have 2 squared terms. The last term is 1 by 2 cubed. So when I have 2 squared terms in the denominator, I will have 2 cubed. Similarly, 1 by 9 to 1 by 16, I have 2 cubed terms, 8 terms, and then in the denominator I will have 2 to the power 4. So, the last term will be 1 by 16. I hope you are getting the pattern right, and in the last set of parentheses that I have formed here, obviously it is an infinite series, but for the fourth set of parentheses I have 2 to the power 4 terms, and the last term is 1 by 2 to the power 5, which is 1 by 32. So, what will happen if I am talking of the nth pair of parentheses? How many terms will there be? There will be 2 to the power n terms. The last term will be 1 by 2 to the power n plus 1. 2 to the power n minus 1 terms will be greater than 1 by 2 to the power n plus 1. So, you can just put the video on pause and go slow with this if it takes a little more time to absorb, but it is absolutely fine. And here the last term will be equal to 1 by 2 to the power n plus 1, right. So, you have a total of 2 to the power n terms, and together the sum will be strictly more than 2 to the power n divided by 2 to the power n plus 1, right. And that again, if you notice, that is nothing but half. So, what is happening? We have a harmonic series and its sum is larger than an infinite number of halves. So, here we have a series that diverges. The important lesson here is that the nth term for this series tends to 0, but the series does not converge, it diverges. So, the nth term tending to 0, remember, it is a necessary condition for convergence, it is not a sufficient condition. So, now the question is what are the workable criteria that you could use? Is there any workable criterion that we could come up with? And yes, we have a very nice result that emerges from the result that we just laid out, and this is very important for you because this will be the basis for how you will do your problems. Now see, if you remember your section on logic, when proposition A implies proposition B, that is equivalent to saying that not B implies not A, right. So, if A1 plus A2 and so on, if this general infinite series converges, and that implies that the nth term in the limit must be 0, then we can write not, so A is our left hand side proposition, B is the right hand side proposition. So, we can say that if the nth term in the limit, if the nth term as n approaches infinity is non-zero, then the series will definitely diverge, right. So, not B implies not A. This is the result that you are going to use when you solve your problems. If you find that the nth term in the limit is not 0, then you will definitely conclude that the series diverges. In fact, this result also applies to a geometric series, but then for the geometric series we have already established very clear-cut convergence criteria. So, you may or may not use it, but this is the result which you must keep in mind. And one more result before we end this first part of the lecture. This is also another result that you can use, that if you have a series of the form summation 1 divided by n to the power p, then this series is convergent as long as p is strictly greater than 1. Note that there is an equivalence relationship here. So, summation 1 by n to the power p is convergent, is equivalent to saying that the power, the exponent here p is strictly greater than 1. We will see how all of these results are used when we practice some problems in the second part of the video. That's all from me for this first part. Thank you so much. Take care.